Paper 1, Set 2, Specimen Set 2. Question number 3.1. The electronic configuration of iodine. Now iodine's a big atom, so they've given you Kr, krypton, which is the full, the electronic configuration of an atom that has a full electronic configuration to the right in the periodic table in period 4. So in other words, you've just got to fill out the 5th energy level of electrons. So it'll go 5s2, 4d10, 5p5. How do I know that? Well, I know when I put 4 s's in, I backfill the 3d's. So after 4s, there's 3d. So the same thing happens in period 5. When I put 5 s's in, I backfill the 4d's. So I fill up all the 4d's, they can have 10 electrons, and I know that iodine's in group 7, so it's going to have 7 electrons in its outer 5th energy level, so it'll be 5s2, 5p5. You can add up the number of electrons in krypton and add on another 17 for those that you've just put in 5s2, 4d10, 5p5, and you'll come out with the same number of electrons as in iodine. Tricky question this. You don't seem to be given enough data. One clue is that you're not given Avogadro's number in the question. You're not given distance. You're not given velocity. You don't seem to be given enough data. So there's a trick to this question. The M mass is the mass of one particle in kilograms. So what you have to do is you have to find the atomic mass of the particle. Say, for example, if in the question it was 82Q, whatever Q is, it's a fictitious element. And you have to divide that number. 82 grams would be 1 mole. You'd have to divide 82 by Avogadro's number to get the mass of one particle, rather than a mole of particles, in grams. Then you have to divide by 1,000 to get into kilograms. But you're not given Avogadro's number. So there's a trick to this question. This is the trick. The kinetic energy of all particles in a time-of-flight mass spectrometer is the same. So kinetic energy it gives you is half mv squared. So half mv squared for the 82Q particles must equal half mv squared for the 86Q particles. Multiply each side by 2, so mv squared for 82Q equals mv squared for 86Q. Then what I've done is I've put the number 82 in as the mass and 86 in as the mass for the two particles 82Q and 86Q respectively. Now, I could turn those into, instead of 82, which is 82 grams for 1 mole, I could convert that into the mass of one particle of each by dividing both sides, because you'd have to do the same on both sides, by Avogadro's number to work out the mass in grams of one particle of 82Q and one particle of 86Q. But why bother? Why divide by Avogadro's number on each side? There's no point doing the same thing on each side. Similarly, I could get that then into kilograms for one particle by dividing by 1,000. But what's the point? So I've just left it the same. It'll still work out. V squared it gives you is d over t. The d is the length of the tube, t is the time of flight for that particular particle. But the length of the tube isn't changing, so I've cancelled d on each side. And I'm left with 82 divided by t squared for the 82 particle equals 86 divided by t squared for the 86 particle. I'm given the time of flight for the 82 particle, so I'll plug that in. And then I've rearranged the equation, got t squared for 86Q, and I've square rooted it, and so the time of flight for the 86Q is 1.27 times 10 to the minus 5.